This is seventh week of the problem solving session for the course Applied Thermodynamics. So this is the last week on the module of internal combustion engines. So we have looked at how the engine works, how the cycle in which it operates, the different cycles like auto cycle, diesel cycle, dual cycle. We saw how it works, and we also solved some numericals on how to solve the cycle to find out the work produced. We saw integrated power, brake power, friction, act of friction, the combustion, how combustion is affecting. We also calculated the reaction, chemical reaction, to find out the mass of fuel and the equivalence ratio, everything. In the last module, we'll see some on combustion, what happens, how much when it is fired, and now what is the velocity of flame, and how the combustion, numericals on combustion basically. And then we'll also see heat transfer between the engine and the environment. You will always have some amount of heat which is lost because it's at higher temperature, and various interactions because of that, how the engine performs. We will see some numericals on that. And also previously we saw knocking. So in the process of combustion, we also see that when the flame should be retarded, so the flame should go out, so it should go out near the walls, it should not go out in between, so there will be incomplete combustion. And we'll see some numericals on the flame, how to calculate those, and at what velocity the flame is traveling, how much time it takes, at what angle the flame is initiated, numericals related to that. And also we'll see exergy analysis of an internal combustion engine. We know previously in Rankine cycle we did some numericals on exergy analysis. So similarly we'll see on numerical on how to do an exergy analysis of a internal combustion engine. So I have taken a numerical for an auto cycle. Similarly you can take for different other cycles. So basic ideas for the internal combustion engine. So it will have some energy which is you are providing, and you are utilizing that energy to produce some work. And how much better the engine is, you can produce that much amount of work, and you can increase exergy efficiency. So this analysis is useful to see where exactly you are losing energy, and what kind of measures you can take to increase the efficiency of the engine. So as you could have seen in the lectures, that the turbochargers which are used, basically two types of chargers are used. One is supercharger or turbocharger. Superchargers, you use the work generated in the engine to run the supercharger to compress the inlet fluid air which is going into the internal combustion engine. In turbochargers, what you do is you know that in the exhaust gas which is going out of the internal combustion engine, it takes away a large amount of energy, because this exhaust gas after combustion, it is at very high temperature. So when it goes out, you are losing energy in the sense when the exhaust energy is going out. So it also carries a significant amount of energy with it. So you can utilize this energy to run your auxiliary, since in this case a turbocharger. So you can generate work. In sense, if it's at a higher temperature, you can run a engine between that and ambient to generate some work. So in this case, what you're utilizing it to run a turbocharger. This turbocharger utilizes the exhaust gas, and it runs and compresses the inlet air. So this is beneficial. It will increase your efficiency of the cycle. And unless the supercharger, which utilizes the brake power which is generated, you're generating power from the exhaust. So in that case, is more advantageous in that sense. So this all came with the exergy analysis. So we'll see a numerical on exergy analysis, and also on combustion, as well as heat transfer in this engine. So heat transfer, in sense, you ambient is at 35 degrees, and your inlet maximum it can reach from 2500 3000 Kelvin. So you have a large temperature difference. And inside too, when the flame is propagated, the flame initiation, there the temperature is large, and near the wall it will be less. So in wall to gas there will be convective heat transfer, and then the inner wall to outer wall there will be conductive heat transfer, and then conduction happens between the outer wall and the ambient. Uh, this this is also required to design your cooling systems. So in air cooled system like engines which are used in motorbikes, you have fins placed outside, so it will take care of cooling the engine. So these are used because you need to avoid hot spots which can in sense fuel is coming in, it can create knocking, and because it can self ignite, your temperature is so high. So to avoid that, and also to design your cooling system for efficient performance of the engine, so you need to do this heat transfer analysis of an internal combustion engine. So we'll see some numericals on internal combustion as well, sorry, heat transfer in IC engines. So proceeding, so we'll see some MCQ type questions at the start, and we'll look at some numerical problems later. So starting with, we have during the idling process, a petrol engine usually requires rich mixture. Is this statement true or false? So that's during idling process, a petrol engine is a spark ignition engine, so usually requires a rich mixture. So this statement is true. Idling process is a process in you see, you switch on your suppose you if you're running a bike, so you switch on and you are not you say bike is on a neutral or a car is on neutral, so you have not applied any gear or you are not moving, so you are still steady. Or suppose you are waiting in your signal, there's a red signal and your car is parked, and but your engine is on. So this is kind of an idling process, because the engine doesn't have any load, so it's running freely. You are not applying any load to the engine, so this is an idling process where there is no load on the engine, so brake power is zero, you are not utilizing any work. So during this process, will the engine require a rich mixture? This is true. We'll see the reason. So idling process, engine operates under no load condition and with nearly closed throttle. So what happens is, when the engine you're taking in fuel and its combustion happens, a large amount of exhaust gas is retained inside the cylinder compared to when it's in moving condition, because the throttle is nearly closed. So when the fuel air mixture enters, so your with the presence of exhaust gases, this mixture, as I explained, the mass of exhaust gas in the cylinder at the end of exhaust stroke remains fairly constant throughout the idling process. So exhaust gas which is going out is remaining constant. So amount of fresh charge that enters the cylinder is less compared to that during full throttling. So exhaust gas remains mixed with fresh charge admitted to the cylinder. So to sustain the combustion, you need a rich mixture to be entered compared to when it is running. So thus engine requires a rich mixture for starting and idling to compensate for the charge dilution. So this fresh charge which you are coming in is actually less, so and it will come and mix with the exhaust gases. So what happens to this exhaust gases, if it's fully combust, it cannot react with the fuel, so you need air for the combustion. So this will create a dilution, and to sustain the reaction you need a rich mixture. If you send in a lean mixture, what will happen is the initial mixture fresh charge which is coming in, the fuel with the air, it's already lean, amount of fuel in the air is already less, and less amount of air is coming in, less amount of charge, because throttle is nearly closed. So what will happen is, now this is getting diluted again with the exhaust gas which is present in the cylinder, and that can happen that engine may cease to combust and it can stop. So to avoid that, you will send in a rich mixture. So hence during the idling process you require a rich mixture. So next question is, by higher octane number of spark ignition fuel, it is meant that the fuel has dash. So higher octane number of a sparking ignition fuel. So it is meant that the fuel has dash higher heating value, higher flash point, lower volatility or longer ignition delay. So the answer is D, longer ignition delay. So this generally means that this will avoid knocking. So at lower temperature, your ignition delay when it's reach self for the flame to propagate and to combustion to happen, to propagate and for combustion to happen, that time is very large when your octane numbers are high. This is opposite when your CT numbers are high. You require in compression ignition engine, you require this ignition delay to be very less. So that's self ignition can happen. But you don't need that in spark ignition fuel, because you are providing a spark and initiation for the combustion. So hence you require a longer ignition delay. You don't require ignition to be happen by itself. So it will create knocking. So you don't require that. So you require a higher octane number. So this higher octane number represents that you have an higher ignition delay. If your temperature is increasing, your ignition delay will keep on reducing, and you can have self ignition. So even in spark ignition engine, if your engine temperature reaches very high, it will create knocking. It will create ignition can happen because your ignition delay will reduce at higher temperatures. So higher octane number represents that it has a longer ignition delay, and the opposite is true for cetane number. So the next question is, a gas engine has a swept volume of 295 centimeter cube and clearance volume of 22 centimeter cube. Swept volume is 295 centimeter cube and clearance volume is 22 centimeter cube. So they are given, and they have also said that its volumetric efficiency is 0.82 and mechanical efficiency is 0.91. So the volume of mixture in centimeter cube inductor taken in per stroke is. So what has been asked is the volume of mixture, air plus fuel mixture. What has been asked. So there are many unnecessary values which are given. We don't require clearance volume, we don't require mechanical efficiency. Mechanical efficiency is brake power by indicated power. So how much power is you are getting with the power generated. So that's what is mechanical efficiency, and volumetric efficiency is what is required in this case. Volumetric efficiency is mass of fuel coming in divided by the mass in the swept volume. So that's what we require. So if your densities are nearly same, you can cancel out density and you can write it in terms of volume. So volumetric efficiency is actual volume by swept volume. Actual volume is the volume of air coming in into the cylinder. So actual volume by swept volume. So swept volume we already know in the question, it's 295 centimeter cube, and the volumetric efficiency is 0.82. So using this relation we can find out the actual volume. So actual volume is 0.82 times 295, which will give us 242 centimeter cube. So the answer is B, 242 centimeter cube. So moving on, which of the following statements are correct? So are can have multiple correct answers. Is and are is given. So we can have multiple correct answers. So starting with A, higher compression ratio in diesel engine results in higher pressure. So this is true. If you are having higher compression ratio, your volume is less. So you know that for an ideal, assuming air to be an ideal gas, PV is constant. So pressure is inversely proportional to volume. So when you compress, if your compression ratio is high, your volume at the state 2 after compression will be very less. So that will create an increase in pressure. So your pressure will be higher in that case. So statement A is true. Higher compression ratio in diesel engine results in higher pressure. That is required too in a compression ignition. If you have higher pressure, your temperature will also be higher, and it will create self ignition. That's what you require. Compression ignition will create. That's what you required in a diesel engine, which operates in a compression CI engine, compression ignition engine. So hence statement A is true. The next statement given is petrol engine works on auto cycle. This too is true. Auto cycle is similar to spark ignition engine, and petrol engine works on auto cycle. This statement 2 is also correct. Then statement C is compression ratio for petrol engine varies from 6 to 10. So this 2 is also correct. 6 to petrol engine compression ratio is generally in 6 to 10, and your diesel engine will be close to 14, in the range of 14. So this statement is also correct. So all three statements are correct. A, B and C are correct. So we'll see the next one. The next question is, which of the following component is not an integral part of a SI engine? Which of the following component is not an integral part with an SI engine? A, spark plug. B, ignition coil. C, fuel injector. D, carburetor. Sorry. So SI is spark ignition engine. So you need to create a spark for combustion. So for that you generate spark in the spark plug. So you require a spark plug, and the spark plug contains an ignition coil, and that too is also true. So you require for spark ignition spark plug and ignition coil, both are correct. Then fuel injector, you don't require a fuel injector because your fuel already charge which is coming in, air which is coming in will contain fuel and air as a mixture. So this is combustion is ignited with a spark plug. So you don't require a fuel injector as such for fuel to be injected in the process. So fuel injector is not required. Then it's a carburetor. Carburetor is a device used for mixing air and fuel. So D is required because in spark ignition engine you require the air which is coming in to contain fuel as well as air. So the mixture should come is produced in the carburetor, and it is provided to the internal combustion engine. So carburetor is also required. So the only component which is not required, which is not an integral part, is the fuel injector. So the answer is option C. So moving on, the question is the octane number of isooctane is taken as dash. So this if you remember, this is a benchmark which is set. So octane iso number comes from the octane there. So this value is 100. So octane number of isooctane is 100. So answer is option C. So the next question is, the accumulation of carbon in a cylinder results in increase of dash. So the accumulation of carbon in a cylinder results in increase of dash. A, ignition timing. B, effective compression ratio. C, volumetric efficiency. D, clearance volume. So accumulation of carbon in a cylinder it can happen because carbon, when this carbon is produced, if you have cracking of oil, the lubricant oil which is coming in, or there's an incomplete combustion, so that you produce carbon soot particles. So this will get accumulated in the cylinder, in the piston, near the piston ring, piston cylinder arrangement. So this will affect some of the parameters mentioned here. So this carbon will keep on depositing because of incomplete combustion, and the lubricating oil which is coming in for lubricating the piston and cylinder close arrangement. So that will affect the effective compression ratio. So when carbon deposit accumulate on the cylinder head, so they reduce the volume of the combustion chamber. So now the piston accumulating. So, if you assume in internal combustion engine, you have the cylinder arrangement and you have a piston. So the piston is what is moving. So now the carbon is getting deposited on the piston head. So effectively, the volume which is there is getting affected, because initially some amount of volume was there. Now some, after depositing some amount of carbon on the piston head, this effective volume has reduced, which was available in previously. Now the volume of the carbon which is accumulated on the piston, that amount has been reduced from the initial volume. So this effectively reduces the compression ratio. This is what the major effect. If you see, the clearance volume will also get affected, but the major in volume, it will affect some effect to the volumetric efficiency, but it will affect majorly the effective compression ratio. So this reduction in volume will increase the compression ratio in the engine. So moving on to the next question, what is given is, in order to eliminate knocking in compression ignition engines, there should be dash: short delay period for the fuel, late auto ignition by the fuel, high self ignition temperature of fuel, low compression ratio for engine. So what can be done to eliminate knocking in compression ignition engines? That is the question. So short delay period for the fuel is the answer. So you are essentially reducing the ignition delay time. This will create that there will be self ignition in the diesel engine. That's what is required, and having this short delay will create flame and will get propagated, and it will create a uniform combustion which is required. So in compression ignition engine or CI diesel engine, you have require the fuel should have a shorter delay period, ignition delay. That's what having higher C10 number. So you need a higher C10 number. So the next question is, the spark plug is fired at 18 degree before top dead center. So this is regarding a spark ignition engine, or assume a petrol engine. So you have a spark plug, and during combustion, so you take in charge fuel plus air mixture. This the piston moves down and it will start compressing. So in theoretically, what cycle which we solved previously, assuming an idle air cycle, air standard cycle, what we say is, after reaching the top dead center, heat is added, the combustion takes place at constant volume. But that is not possible practically. So you fire and as the fuel also has some delay in the flame to generate and it to propagate. So that it requires some time. So what you do is, you fire the spark plug before it reaches the top dead center. And it also requires some amount of time for the whole combustion to take place. So that's what all is calculated using the valve timing diagrams and the spark plug ignition which is taking place. So here they are saying that now the air plus fuel air mixture which is coming in, it's the piston goes down and it starts compressing. So at the top of the top dead center, it has reached the total compression, and it will ignition will start. So practically what will happen, when this compression process is taking place, you ignite a spark. So this is ignited 18 degrees before in terms of the crank angle. So 18 degrees before it reaches the top dead center. So that's what is given. The spark plug is fired at 18 degrees before TDC in an engine running at 1800 RPM. So it takes 8 degree of engine rotation to start combustion. So that is the delay period, and get into flame propagation mode. Okay, so and then the flame termination occurs at 12 degrees after top dead center. So after before 18 degrees before TDC, so your spark plug is initiated. So it takes 8 degrees of rotation of the crank angle. So 10 degrees before TDC, the flame is started propagating. It takes from 10 degree before TDC to 12 degrees after TDC. That is the combustion time it requires for in terms of crank rotation, and at 12 degrees after TDC, so the piston has reached and it started expanding again in the power stroke. So during that 12 degrees your flame has reached the cylinder walls and the total combustion has taken place. So that was what is given. The spark plug is fired 18 degrees before TDC in an engine running at 1800 rpm, and it says that it takes 8 degree of engine rotation to start combustion to go into flame propagation mode, and the flame termination occurs at 12 degrees after TDC. They say the bore diameter is 70 mm and the spark plug is 8 mm offset from the center line of the cylinder. So bore diameter is the engine cylinder diameter is 70 mm, and they say the spark plug is kept 8 mm away from the center of the cylinder. So offset is 8 mm. So from the center of the cylinder. So calculate the effective flame speed. So we'll see how to calculate this. So we know that the total time for combustion. So as I told previously that 18 degrees before TDC, so there is 8 degrees delay. So 10 degrees before TDC the combustion is starting, the flame started propagating, and from 10 degrees before TDC to 12 degrees after TDC is where the combustion ends. So now 10 plus 12, so 22 degrees the crank rotation angle is what is the time it takes for the combustion to take place. So the time taken for combustion is 20 degrees divided by 360 degrees, because crank rotation is 3360 degrees, in which 22 degrees is what the combustion time in terms of crank angle is. So that divided by the rotation speed, we are converting 1800 rpm to revolution per second. So 1800 divided by 60, so this will give me 0.00204 seconds. So this is the amount of time, that is 2 milliseconds. 2 milliseconds is the time taken for combustion to take place, whole combustion to start and end. So in 2 milliseconds the total mixture is getting combustion and chemical reaction has happened. So after that, to find out the velocity or the flame speed, we need to find out the distance traveled. So as the spark plug is not at the center but it's at offset, so 8 mm it's at offset. So the maximum distance the flame has to travel is bore diameter by 2, which is the radius of the cylinder, plus that offset. So that is the maximum distance which will take. At that point is where the combustion will end, and minimum distance will be the other side where this flame would have already reached, and you need the combustion to full combustion to take place. It should have also end at the maximum distance, far away distance from the spark plug, and this far away distance is bore diameter by 2 plus the offset, because it's not at the center, the spark plug is not at the center. So radius of the cylinder plus the offset. We know that the diameter of the cylinder is 70 mm, so 0.07 in terms of meter divided by 2 plus 0.008, this is the offset distance. So the maximum flame travel distance is 0.043 meter. So this gives me effective flame speed as velocity is distance by time. So 0.043 divided by 0.00204, this will give me 21 meters per second. So the answer is option B, 21 meters per second. So the next question is, with increase in the speed of SI engine, the crank angle required for flame propagation is affected. So when the speed of an spark ignition engine is increased, so or the amount of time for the flame propagation to take place is affected with the crank angle. So the time basically is it affecting that? That's what the question is. So the answer is false. So suppose if the engine speed is doubled, flame to traverse the combustion chamber is halved. So the time required for combustion to happen is reduced. So this so what happens is the speed is doubled, because the engine is running. If the speed is doubled and the time required is reduced into half, what happens is it'll give me the same amount of this crank rotation, because these are opposing parameters. So the crank rotation in terms of degrees will remain same for flame propagation. So the crank angle will not be affected with the speeds. So the crank angle required for flame propagation, which is main phase of combustion, will remain almost constant at all speeds. This is an important characteristic of a petrol engine. So what's happening is your speed is getting doubled and your time is reduced in half. So your amount of time taken, amount of the crank rotation will remain same. It will be irrespective of the speed. So the statement is false. So now we'll move on to see some numericals on combustion and heat transfer. So we'll see some starting with some problems on heat transfer. So here what is given is compute the overall average heat transfer coefficient HO and heat flux Q for a single cylinder engine with a 0.1 meter bore and stroke. So this is a square engine, so your bore and stroke are of same length, so 0.1 meter. So we have to find out average heat transfer coefficient and heat flux. They are saying that average combustion gas temperature is of 1000 Kelvin. So average combustion temperature is given as 1000 Kelvin. Coolant temperature of 350 Kelvin. So outside, this being an engine, outside is your water cooled, so or coolant, can be water plus glycol or other mixture. So that coolant is at 350 Kelvin, and fuel airflow rate of 2 into 10 power minus 3 meter cube, 10 power minus 3 kg per second. So this includes the fuel plus air mixture. So this combined mixture mass is 2 into 10 power minus 3 kg per second. So that is, or 2 grams per second. That is what the fuel air mixture is entering. Mass flow rate. So mass flow rate is 2 grams per second. So and assume K value, thermal conductivity of cylinder is 0.06 watt per meter Kelvin, and mu 20 into 10 power minus 6 Newton second per meter. Now K of fluid. The combustible gas is 0.06. K of combustible gas is 0.06. So now all parameters are given. So we need to find out heat transfer coefficient and heat flux. To find out heat transfer coefficient, we'll use the relation given for Nusselt number. So Nusselt number into constant raised to power RE raised to power n. So constant is given as 10.4 and RE raised to power 4 is 0.75. So we'll use that relation to find out the Nusselt number, and using Nusselt number we can easily find out the heat transfer coefficient. To find out in the relation for Nusselt number equal to constant RE raised to power n, we need to find out the Reynolds number. So this Reynolds number is given as mass of air plus fuel mixture into bore diameter divided by the area of the cylinder and into viscosity. So we know the fuel air mixture mass flow rate, which is 2 grams per second, and we also know the diameter, and the area you can calculate pi d square by 4, and we also know the viscosity value. So on substituting that, we'll get Reynolds number as 1274. So now we know the Reynolds number, Now we substitute that in Nusselt number relation, nu equals to 10.4 into Reynolds number raised to power 0.75. Now Nusselt number can be defined as heat transfer coefficient into bore diameter divided by K, thermal conductivity. So now we can take the bore diameter and the K value to the other side, and we can find out the heat transfer coefficient. So heat transfer coefficient will become 10.4 into K by B or D, this is bore diameter, into Re raised to power 0.75. So we know all the parameters. On substituting, you will get heat transfer coefficient as 1330 watt per meter square Kelvin. So this is an overall heat transfer coefficient, average heat transfer coefficient. So now what will we do is Q dash is Q into AP. So we can find out Q flux is H naught into Tg minus Tc, the gas temperature minus the coolant temperature. So we know H naught value, which we calculated, 1330 into Tg is 1000 and Tc is 350. On substituting that, we can find out that the heat flux will be close to 0.86 megawatt per meter square. This is assuming that wall temperature is at the coolant temperature, because we don't have any other parameter. So we assume that the wall is at the coolant temperature, and we can find out the heat flux in this relation. It will be close to the value. So the next question is an inline 6-cylinder. So inline is, so cylinders are arranged in a line. It's not put in a V shape or something. It's all in single line. So we have 6 cylinders, and the capacity is of 6.6 liters. So 6 cylinder of 6.6 liters. It's operating on a 4-stroke cycle SI engine with multi-point port fuel injection. This operates at 3000 rpm. Okay, so we have an inline 6-cylinder of capacity 6.6 liter operating on 4-stroke cycle SI engine with multi-point port fuel injection, operates at 3000 rpm. So this, with the volumetric efficiency of the intake manifold runners, can be approximated as round pipe with an inside diameter of 4 cm. So intake manifold is approximated as a round pipe with the inside diameter of 4 cm. So inlet temperature to the manifold is 27 degrees Celsius. So inlet temperature to the manifold is 27 degrees Celsius. Now calculate average velocity and mass flow rate of air to each cylinder using inlet temperature to evaluate properties. So we need to find out average velocity inside that intake manifold and mass flow rate of air to each cylinder. So the next question is Reynolds number in the runner to cylinder 1, which is 40 cm long. Third question is temperature of the air entering cylinder 1 if the runner wall temperature is constant at 67 degrees Celsius. D. Wall temperature needed for the runner to cylinder 3 such that the cylinder air inlet temperature is the same as that of cylinder 1. Wall temperature needed for the runner such that the cylinder air inlet temperature is same as runner, but the runner length is now 15 cm instead of 40 cm. The K value is given. So we'll see how to solve this. So the first question is we need to find out average velocity and mass flow rate of air entering each cylinder. So for one cylinder, displacement volume will be 6.6 by 6 cylinder, because 6 cylinder of total capacity 6.6 liters. So each cylinder will have displacement volume of 1.1 liter, which will come out to be 0.001 meter cube. Now the mass you can calculate as rho into Vd into volumetric efficiency into N. So this n will be n by 2 because this is operating as a 4-stroke cycle, and rho is 1.181 into displacement volume we have already calculated 0.0011, and the volumetric efficiency is given 89%. Sorry, it's not mentioned, but here I think there's a typo. The volumetric efficiency is given as 89%. Then and speed of the engine is 3000 rpm. Because it operates as a 4-stroke engine, we should divide by 2, and converting it to revolution per second, we divide it by 60. So this will give me the mass flow rate as 0.0289 kg per second. So now the mass flow rate for each cylinder is known. We have calculated mass flow rate. Now the velocity in the inlet manifold is m dot by rho a. So we are approximating that as a cylinder of 40 centimeter 4 centimeter inside diameter. So we know rho 1.181 and diameter is pi into 0.04 square by 4. So m by rho a, AV will give me the flow rate, and multiplying by rho it will give me mass flow rate, just m equal to rho AV. So we are finding velocity using that relation. So velocity will come out to be 19.47 meters per second. So we have first question we have solved. We have found out average velocity and mass flow rate. So second question is to find out Reynolds number for cylinder 1. So this runner length is of 40 meter. So we know Reynolds number is rho Vd by mu. So velocity is known in the intake manifold 19.47. Diameter is known. Inner diameter is that 4 centimeter inner diameter of the runner or intake manifold, 0.04, and density is also known 1.181. Divide by mu is 1.846 into 10 power minus 5. Sorry, this is long length is rho is 40 centimeter. No, just again. Yeah, Reynolds number is rho Vd by mu. So we can find out that d is the diameter 4 centimeter. So 0.04 into 1.181 divided by 1.846 in 10 power minus 5 is the mu viscosity. So it will give me 49825 as a Reynolds number. Now using this, we have been asked the temperature of the air entering the cylinder 1 if the runner wall temperature is constant at 67 degrees Celsius. So if that is the case, what is the inlet air temperature? So for finding that, we need to find out the overall heat transfer coefficient. So we will use the Dittus-Volter relation because this is a pipe flow, and assuming that will be turbulent, we use Dittus-Volter equation to find out Nusselt number. So 0.023 Re raised to power 0.8 into Prandtl number raised to power 0.4. So we know Reynolds number, and Prandtl number is mu Cp by K. So for using air 1.846, Cp value is known, so 1005 by K value is also known, 0.0264. We can find out Prandtl number. Substituting that will give Prandtl number will come out to be 0.708. Substituting this in the Nusselt number relation for Dittus-Volter, we will get that Nusselt number is 114.7. This Nusselt number is nothing but Hd by K. So the K value is known, D value is known 0.04. So we will get H value as 75.2 watt per meter square Kelvin. So now we know the overall heat transfer coefficient. So now we can find out the overall heat transfer which is happening, which is HA delta T, or which will be equal to MCP delta T. MCP delta T is the change in internal energy of the air, and HA delta T is the heat transfer happening between the runner or the inlet manifold with the air. So overall heat transfer coefficient we have calculated 75.2 into area will be the perimeter or the surface area of the tube, which will be pi d into L. So pi into 0.04, which is 4 centimeter, into 40 centimeter is the length of the manifold or the runner for the cylinder 1. So 40 centimeter, so 0.4 this, and we are saying that the temperature of the air entering cylinder 1, if the runner wall temperature is constant 67 degrees Celsius. So runner wall temperature is 67 degrees Celsius, and we know the inlet temperature of the manifold is 27. So 67 minus 27 is a heat transfer happening between the manifold and the air, which will be equals to 0.0289 into 1005 is a Cp value into T naught, air entering the cylinder minus air entering the manifold 27. So inlet minus exit. So amount of energy picked up by the air in the manifold. So this will come out to be T naught as 32.2. So now we know that we have found out the temperature of air entering the cylinder 1. So next question is wall temperature needed for the runner to cylinder 3 such that the cylinder air inlet temperature is same as cylinder 1. Runner length for cylinder 3 is 15 centimeter. So now if the runner length for cylinder 3 is 15 centimeter and you require the same amount of temperature for the air to enter cylinder 3, so what should be the runner temperature? So that is what has been asked. So it will be the same previous relation, 75.2 into pi into 0.04 into 0.15 instead of 40 centimeter is 15 centimeter into wall temperature minus the air temperature. So equals 0.0289 into 1005 minus 32.2 minus 27, because you need the same temperature of air to enter cylinder 3, so it should be at 32.2 minus 27, which is inlet, so it will come in 5.2. So this will give me that the difference in temperature between the air and the runner wall should be of 107 degrees Celsius. So now the wall temperature will be T wall equals to 107 plus 27, the air inlet temperature 27. So your runner should be at, wall temperature should be at 134 degrees Celsius. So previously for 40 centimeter length, the wall temperature was at 67 degrees Celsius. Now for 15 centimeter, for same heat transfer or same amount of temperature entering the cylinder, we require a wall should be at of 134 degrees Celsius. So moving on, the next question is, during combustion there is a momentary heat flux through the wall of the combustion chamber at a certain spot equal to gas temperature in the cylinder at this time is 3800 degree Rankine. So this is given in Rankine, and Q is asked in degree Fahrenheit, and the heat flux is all given is in BTU, British thermal units. So units are different, but we need to find the ultimate aim is to see how to solve the problem. So we'll neglect Rankine, the units can be always be converted. So this is all in British standards. So we'll see. So during combustion there is a momentary heat flux through the wall of the combustion chamber at a certain spot equal to gas temperature in the cylinder at this time. So okay, the combustion heat flux is 67,000. I think I have missed that. I'll make change there. So heat flux is given 67,000, and the gas temperature at that point is 3800 degree Rankine, and the convective heat transfer coefficient within the cylinder is convective heat transfer coefficient also is given. I think well, there's some values are missing. Okay, I'll make change there. Then coolant temperature is 185 degree Fahrenheit. Thermal conductivity of the 0.4 inch thick cast iron cylinder wall is So thermal conductivity of wall is also given as 34 BTU, British thermal unit, divided by R feet degree Rankine. So we have asked to find out inside surface temperature of the cylinder wall, B surface temperature on the coolant side of the cylinder wall, convection heat transfer coefficient on the coolant side of the cylinder wall. So inside surface temperature, outside surface temperature, and convective heat transfer coefficient on the coolant side. So this is three thing we have to find out. So as a question, the heat transfer coefficient is convective heat transfer coefficient within the cylinder is 22 BTUR feet square degree Rankine. Okay. So Q is heat flux equals H delta T. So H is we know outer temperature, H T combustion gases and wall 1 dt into heat transfer coefficient into area. So we have given heat flux, so not it's not required. So heat flux is 67,000 equals heat transfer coefficient is 22. So 22 into, at this point the gas temperature is at 3800. So 3800 Rankine minus T. T is the inner wall. So we are just seeing the inner part of it with the gas and the inner wall. So what is the convective heat transfer term? So we can find out the inner wall temperature using this relation. So the inner wall temperature will come out to be 755 degree Rankine or 295 degree Fahrenheit. When you convert this from Rankine to Fahrenheit. So now we have calculated the inner wall temperature. Now the next question was to find out the outer wall temperature. So we know that heat transfer, if you take can solve that heat flux will remain same, or heat transfer will remain same if you take any part of it between two temperature, that heat flux will remain same. So now you can we know that heat flux. So if you take it from between the inner combustion gas and the coolant, or if you take it between inner combustion and wall, or between the two walls, this heat flux will remain same. So now we know we have already calculated the inner wall temperature. So using the conduction term for the cylinder, because the heat flux will remain same, we can find out the outer wall temperature. Or you can, the other way around is, you can draw a resistance. We can take this two resistance, conduction and convection, and using the gas temperature we can find out the outer wall temperature also. There too the heat flux will remain same. So for simplification we will just take the cylinder. So heat flux is 67,000, which will be equals to K dt by dx. dt is the wall temperature difference, Tw1 minus Tw2, divided by the thickness of the cylinder. It's actually minus, but I have incorporated dt as the larger value minus the smaller value. Or if you are writing at Tw2 minus Tw1, so there should be a minus sign here, minus K dt by dx. So the difference there and the sign should always be taken care of. Here I have written as higher in Tw1 minus Tw2, so I have put up a positive sign because I already incorporated that. So 67,000 equals the heat thermal conductivity cylinder wall, thermal conductivity of the cylinder wall is 34 BTUR feet degree Rankine, and the thickness is 0.4 inch. So 67,000 equals K dt by dx, 34 into dt, and 0.4 inch we are converting into feet, so divide by 12. So dt temperature difference will be given is 6 degree Fahrenheit. So the outer wall temperature will be Tw2 will be Tw1 minus dt, which will give me 229 degree Fahrenheit. So the outer wall temperature is 229 degree Fahrenheit. Now we need to find out the heat transfer coefficient in the coolant side. So we know the coolant temperature, we know the outer wall temperature. Same relation we can use. We know the heat flux. So Q will be H Tw outer wall minus the coolant temperature. So we can find out the heat transfer coefficient. So we know Q is 67,000 equals H outer wall heat transfer coefficient into wall temperature, outer wall temperature is 229 minus coolant temperature is given as 185 degree Fahrenheit. So 229 minus 185, which will give me heat transfer coefficient as 1523 BTU r feet square degree Rankine. So this was a simple heat transfer problem. So we have found out that all the temperature and the heat transfer coefficient. So moving on, we'll see a reasoning problem. So this is a problem for reasoning. We have two engines. So two engines have cylinders that are geometrically the same in size and shape. So so to speak, we have two identical engines. That's what this is. We have two identical engines, but the cylinder engine A are surrounded with normal water jacket filled with water ethylene glycol solution. So the engine A is water cooled, water plus ethylene glycol solution, which is cooling the cylinder. So that is filled in the water jackets. The cylinder B are insulated. So cylinder B is insulated, so making this an adiabatic engine. So the difference is how the heat transfer is taking place. So engine A is water cooled, engine B is insulated, so it's an adiabatic engine. There is no heat transfer. Other than temperatures, the engines are operated with the same steady state condition. So as much as work. So to find out the difference, so you have identical engine, but just the insulation is different, and you are running it at similar conditions. Now the question is, which engine has higher volumetric efficiency and why? The second question is, which engine has higher thermal efficiency and why? Third question is, which engine has hotter exhaust, why? D is, which engine would be more difficult to lubricate and why? The last question is, which engine would be better spark ignition engine and why? Okay, so we'll go one by one. So the first question was, which engine has higher volumetric efficiency? So the reasoning is, engine A will have higher volumetric efficiency and engine B will have higher steady state operating temperature, including cylinder wall. So because this is adiabatic, previously in engine A you have water cooled, so the water will take away some heat, so it will not raise the engine temperature or the wall temperature and the contents inside. That temperature will not be raised because some amount of heat is taken away by the water. So the internal engine as to speak, that will go down, so as the temperature. So engine A will have a lesser temperature compared to engine B. So what happens is, this will heat the incoming air to a higher temperature, engine B, because the engine B is at higher temperature. So this will heat the inlet air coming in to a higher temperature. This will do is, it will reduce the density of the air coming in. So if it reduces the density of the air coming in, so your mass is coming in will reduce. So effectively your volumetric efficiency will also go down. So volumetric efficiency is nothing but your volume of air coming in divided by your swept volume. If your air coming in density is very less, it will displace larger amount of volume inside, so very less amount of air will come in, so the volume of air which is coming in will go down. So higher temperature, higher density of the air coming in, lower density of higher air coming in because of higher temperature of air, and this will cause lower mass coming in and will reduce the volumetric efficiency. So engine B will have lower volumetric efficiency compared to engine A. The next question was, which engine will have higher thermal efficiency? So higher thermal efficiency is will have is engine B, because there is no heat transfer happening, so there is no very less heat being lost. So heat lost is not energy, the energy heat loss is energy lost, so you are losing energy there. so that is not getting utilized. You can think in that way. So engine B, you are not losing any energy because of adiabatic condition or because of the insulation. So this will have a better thermal efficiency compared to engine A. So we saw volumetric efficiency. Volumetric efficiency, your temperature is higher, so your density will be lower and you'll affect the volumetric efficiency. But what happens is your thermal efficiency is higher because you're losing less amount of energy. So but what happens is engine B will be hotter than engine A, so will be at higher temperature. So what happens is the peak temperature will be also be higher in engine B. So higher temperature means higher efficiency. Q will be at higher temperature is more, the quality of the heat is more. So the higher the temperature at which energy is used, the higher will be the efficiency of that use. So engine B would have to be a CI engine, so it should be a compression ignition engine, because the temperature is also high, so it's better to have a compression ignition engine because the fuel will self-ignite rather than if you operate as a spark ignition, there will be knocking and it will hamper the engine operation. So its walls will be too hot to operate as a spark ignition engine, so the air fuel mixture would self-ignite during compression. So CI engine operate at higher compression ratio and thus have higher thermal efficiency. So that's what, at peak pressure if you fix up, so compression ignition engines are better, the diesel engine is efficiency will be high. So that's what is meant here. So engine B will have higher thermal efficiency compared to engine A. So the next question is which engine has hotter exhaust? Why? So definitely engine B will have hotter exhaust, as I told previously. Your heat loss is minimal or no heat loss because it's insulated, so it will increase the temperature within. So walls, everything will be at higher temperature, so your exhaust will also be at higher temperature. So if you see, it's kind of contradictory because higher exhaust temperature means a large amount of air energy is lost as the exhaust air is carrying a larger air. So this is in opposing nature. So if you see, then it depends upon the fraction of how much it's produced and how much is lost. So ultimately the efficiency will come to how much amount of energy is fraction of energy is lost in exhaust and how much amount of fraction of energy is produced as work. So it will depend on that. So it looks slightly contradictory, but it ultimately comes out to the fraction in amount of work produced. So it does take a large amount of exhaust energy because it's a higher temperature, but the overall work produced also will be higher, and hence the thermal efficiency will be higher for engine B. So engine B will have hotter exhaust. So which engine would be more difficult to lubricate? Why? So definitely engine B will be difficult to lubricate because it's operating at higher temperature. So you're lubricating oil, if your flash point of the oil is very less or flame point, it can combust and the oil can crack and can produce carbon soot particles. So it can have different problems. Thermal degradation, that is called thermal degradation. So there will be problems of thermal degradation of the lubricating oil. So you need a better lubricating oil which will operate at higher temperatures. So you need that kind of oils, so which will be difficult. So hence engine B will be difficult to lubricate. So the next question is which will be better for SI engine? So as I previously told in B, that engine B is better as a compression ignition engine because during compression you have higher pressure and higher temperature in B. So that is suited for a compression ignition engine, which is not suitable for spark ignition because it will create knocking and other stuff. It will self-ignite, so you don't want that. So you cannot operate engine B as spark ignition. So engine A would be a better option for spark ignition engine. So we have done some reasoning to see how the heat transfer between engines is affecting the operating parameters. how it affects thermal efficiency, and some lubrication, how it affects, and what kind of engine should be operated for what kind of situations. So if you have lesser heat transfer, it's better to suit it with compression ignition. If you have more heat lost, a major chunk of heat is lost in spark ignition engine. So that comparison which is been made here. So we'll move on to see some numericals on combustion. Okay, so sorry. So the next question is, we have a 6-cylinder spark ignition engine with a total displacement of 1.86 liters, operates at 2400 rpm using gasoline direct injection with 2 injections per cycle in each cylinder. So we have a 6-cylinder spark ignition engine, so with a total displacement of 1.86 liters per so 6-cylinder of capacity 1.86 liters, and it operates at 2400 rpm, and we use a gasoline direct injection for per cycle. It does 2 injections per cycle in each cylinder, and they say the spark plug is fired at 19 degrees before TDC, and there is a ignition delay of 0.0015 seconds before combustion is established. I'll just clear this up. So gasoline direct injection is just like fuel injection, but this is just an additional techniques which are used currently. It's just like compression ignition, but you use a spark plug in this case, that is different. But the fuel injection is not necessary in a spark ignition engine, but modern engines do use injection in spark ignition engines as well. But this is an additional option, but it's not an necessary part. In the previous MCQ which we saw, the questions which is asked, the others are all required, and this kind of an optional choice. So there we selected fuel injector as an option, which is not an integral part of the spark ignition engine. So that is kind of an optional option that in the modern engines do use, like this gasoline direct injection. So that part I wanted to clear up. Okay, so moving on. The spark plug is fired at 19 degrees before TDC, and there is a ignition delay of 0.0015 seconds before combustion is established. So the delay time in terms of time is given, and the point at which a spark plug is fired is also given. So they are saying, during combustion there is a rich air fuel mixture around the spark plug and a lean mixture in the rest of combustion chamber. So the rich zone can be modeled as a 2 cm diameter hemisphere around the spark plug. This flame speed of 32 meters per second. So around the spark plug, we are assuming that 2 cm hemisphere is there, and that hemisphere outside, this flame speed is 32 meters per second. So the lean zone then fills the rest of the combustion chamber to the outer edge of the bore, and flame speed of 19 meters per second. So the outer edge near the lean mixture is, this flame speed is 19 meters per second. So the engine has a compression ratio of 9.8, a stroke of 7.20 centimeter, and a connecting rod length of 13.3 centimeter. It is spark plug at the center of the combustion chamber. So this is the parameter values which has been given. We know the flame speed, the compression ratio, the stroke length, connecting rod length, and so on. What are we asked to calculate is crank angle position at the end of combustion, piston speed at the end of combustion, volume in combustion chamber of one cylinder at the end of combustion. Okay, so we'll see. So first, bore can be calculated as follows. So displacement volume for each cylinder is total number of cylinders, 6 number of cylinders into pi by 4 b square s. So we know swept volume, so which is stroke, is 7.20 centimeter, So converting that into meter and substituting, we can find out the displacement volume is 1.86 liters for 6 cylinders. So substituting, we can calculate the bore length as bore diameter of the cylinder is 7.4 centimeter. So now time for flame to reach outer edge of fuel rich zone is distance by velocity. So now we know that the rich zone is the model as a diameter of 2 centimeter diameter. So 0.02. Now distance will be the radius. So because this is a hemisphere, to reach outer, the distance is a radius. So 0.020 divided by 2 divided by the flame velocity given is 32 meters per second in the rich zone. So time taken in the rich zone is 0.000313 seconds. This is the time taken for combustion to happen in the fuel rich zone. Now time for travel to take place in the fuel lean zone. So now lean zone is your bore diameter divided by 2, the radius of the cylinder, minus the radius of the fuel rich hemisphere. So 0.074 is the diameter, minus 0.02 meter is the hemisphere. So divide by 2, that is the distance for the lean fuel zone distance, travel distance. So that divided by velocity of the flame in the fuel lean zone, which is 19 meters per second. So that will give me time as 0.00142 seconds. So now the total time for the combustion to take place with from the the total time taken for the combustion to end from the spark ignited is, we know the ignition time plus the fuel flame combustion time in the fuel rich zone and combustion time in the fuel lean zone. So idle time, ignition delay time is 0.0015 plus 0.000313 and 0.00142, which will give me 0.00323 seconds. So this is 0.00323 seconds. And now crank angle rotation during combustion is, we know that which running at 2400 rpm divided by 60 will give me per second and into 360 degrees. So that is the amount of rotation which is taking degree rotation into time, which will give me 46.5 degrees. So for 1 second it will go through some amount of rotations into 360 degrees. So that amount of degree rotation the crank is taking place. So amount of degrees it rotates for 0.00323 is the total number of rotations, angle rotations into the time, which will give me 46.5 degrees. So the crank angle position at the end of combustion will be, we know that the spark is ignited at 19 degrees before TDC. So 19 degrees before TDC, so 46.5 minus 19 will give me 27.5 degrees. So after 27.5 degrees after TDC, the combustion would end. So at that position it will be 27.5 degrees after TDC. So the next question is to find out the average piston speed. So average piston speed we can find out as 2 into stroke length into n. Piston speed at the end of combustion. So for that we'll use the velocity relation with respect to crank rotation angle. So piston speed, average piston speed is 2 into s into n, 2 strokes per revolution, and stroke length is 0.072 meters per stroke length into n is 2400 divided by 60. So which will give me 5.76 meters per second. So now the crank offset is s by 2 So is 7.2 divided by 2 equals 3.6 centimeter. Now piston speed at the end of combustion is R by A. R so we know the connecting rod length is 13.3. So 13.3 divided by A is crank offset is 3.6, which will give me 3.69. So using the velocity relation with respect to average velocity is given as UP by average piston speed is pi by 2 sine theta into 1 plus cos theta divided by r square minus root of r square minus sine square theta. So we know the crank angle at the end of combustion is 27.5 degrees. So substituting that, we can find out the piston speed at end of combustion as 5.18 meters per second.